Alright, in this video we'll go over specific discrete probability distributions. So in total we will discuss 6: the discrete uniform, the binomial, hypergeometric, geometric, negative binomial, and Poisson. But in this video number 1 we will focus mainly in the first 3 distributions: discrete, uniform, binomial, and hypergeometric. Now, in the discrete uniform case, as the name indicates, uniform means that all the outcomes, they will have the same probability. That's why when we find the probability mass function, PMF, for probability distribution, is going to be equal to 1 over k, where k is the number of possible outcomes. So if there are 5 outcomes, then it's going to be equal to 1 over 5, because all of them will get the same probability. Now, that's the PMF. In regard to the expected value and the variance, you always have two methods. You can use the general equation that we covered in previous videos. Remember, for the expected value, it's just the probability of each x. So it's x times the probability, the sum of that, right? Since here the probability, it's a constant, it's the same for every single outcome. So you can rewrite the expression as this. Or, as you will see in this video, there are some specific equations that will apply to every single probability distribution. For the uniform case, the second approach will give us this equation, right? Where b is the highest value and a is the lowest value of the random variable. Same thing with the variance. There is a general equation, right? So it's, remember, the difference between each variable outcome minus the mean value square. Then we multiply that times the probability, but here the probability is 1 over k. That's why, because it's the same for the uniform. Or there is a specific equation for the uniform that it's in terms of a and b, like this one: b minus a plus 1 squared minus 1 divided by 12. So you gotta be careful, because these two equations that are in option 2, they do not apply for other probability distribution. They only can be used in the case of the uniform, right? So be careful. Let's check an example. When you roll a die, then let's find the PMF, expected value, and variance. So in the case of the probability mass function, remember that the equation is 1 over k. So here, k, there are 6 outcomes, so it's 1/6, and it's the same probability for every single value. That's the PMF. Now, the expected value, there are 2 options. So we can use the general equation, which is variable times probability plus variable times probability plus variable times probability, the sum of that, right? So that's the general equation, it's 3.5. Or we can use the specific equation that is right here, we covered in the previous slide. So it's b plus a divided by 2. So here b, it's the maximum value 6, a is the lowest value of the outcome 1 over 2, that's 3.5. Of course you get the same answer. We get the same answer. In the case of the variance, same thing, there is a general equation. So we have x minus mu squared for every single value times the respective probability. Since here is the same, it's 1/6. Or you can use the expression for the variance, so it's b minus a. b minus a will be 6 minus 1 plus 1, that's 6 squared, 36 minus 1, 35, 35 divided by 12, which has to be equal to 2.92, right? 36 divided by 12, it's 3, so 35 divided by 12 should be close to 2.92. So there you will get the same answer. Alright, so let's check a second probability distribution, the binomial distribution. So it comes from a Bernoulli process. A Bernoulli process is an experiment where we repeat a trial several times. So usually n refers to the number of trials, and in each trial we will have 2 possible outcomes. So we will label them as failure or success. Imagine that one trial, we're trying to hit a target here. So we're shooting something and we try to hit this point in the middle, right? So if you shoot the point, then you hit the target, that's a success. But if you hit somewhere else, then that's a fail, right? So the meaning of trials is like we can try to shoot to the target 5 times, right? But in each trial or each shooting, then there will be 2 outcomes. Either we get a success or a fail, right? So that's the idea of the binomial distribution. This type of outcomes, this type of experiments where there are 2 outcomes, each trial is independent to each other. That means that the probability of success of one trial won't affect the probability of success of the other trials. They are independent. That's one of the properties of the binomial distribution. So in general, the probability of success will be denoted by P, and the probability of fail, it's Q. This is the complement. Q is 1 minus P, right? Okay, so what is the random variable? And this is important in this unit. You always, once you're given a problem, you always need to identify which is the random variable. That's everything, because once you interpret the random variable and you know the meaning, then you can easily identify which is the right probability distribution to model the problem. So in this case, the random variable x, it's will refer to the number of successes in n trials. Again, here in the binomial distribution, x will be the number of successes in n trials. So there is a general equation for the binomial. So it's from n trials, we get x successes. So this is times the probability of success to the power of the number of successes times the probability of fail. This is the complement this is 1 minus p, remember, q, to the power of the number of fails. N minus x is the number of fails, right? So let me I want to give you like a better idea why we're using this equation, because it may be a little bit confusing. I don't want you to memorize the equation. So imagine that we're using the same example that I just mentioned in the previous slide. So we imagine a trial, so we're going to hit 5 times, and the idea is to hit the circle in the middle, right? That's it. And there is a probability to hit the circle. I'm going to say it's 0.1. So in every single shooting, there is a probability of 0.1 to hit the circle, or 0.9 is the complement, the probability that you will hit somewhere else, right? Inside that circle. Alright, so I mean that I want to find the probability that we hit probability of x equal to 2. That's the probability that we'll hit the circle 2 times, exactly 2 times out of the 5 trials, right? So that might happen in different ways. So imagine that one possibility, this is just one option, is that we hit the target in the first two shootings, and then in the other 3 we missed the target, right? That's an alternative. So let me write it down. So what's the probability of that scenario? They are independent. So the probability of that scenario, it's going to be 0.1, that's success, again success, times then fail. This is 0.9, 0.9, and 0.9, like 5 shootings, right? Because n is equal to 5, and there are 2 successes here, right? And 3 fails. Now, the problem here is like this is only accounting for one scenario, where the 2 successes are in the first 2 places, in the first 2 rounds, in the first 2 trials. But we want to make sure that we account for every possibility. So we need to make sure that we can get all the scenarios where the successes are combined in the 5 options. That means that we might get a success in the first one and one success in the last one, and not always in the first 2 positions. So if you notice this structure from here, this is what we're doing. P to the power of x, so it's the probability of success to the power of the number of successes. So here, for example, we have 2 successes, right? So this is like 0.1 to the power of 2. 0.1 to the power of 2. That's the x, right? 2 successes, right? In the example that I'm using. Then we have q is probability of fail, that's times 0.9 to the power of n minus x. So n minus x is the number of fails. So we have 5 trials, 2 successes, then there are 3 fails in this experiment, right? So far we're following the same structure. But now, how do we make sure that we get all the possible scenarios, not only that scenario where the 2 successes are at the beginning? That's why we use this combination right here. So the combination will take, okay, the number of positions or the trials, 5, and then it's gonna pick the number of successes, 2 successes. So in that way, it's gonna make sure that we are accounting for all the possible scenarios, because in those 5 positions, we're gonna take 2, right? So that's the meaning of this equation. You don't need to memorize it. If you know what it means, then I'm pretty sure that you will use it without any problem. Okay, in the binomial distribution, we can also find the expected value and the variance, again using general equations, or there are some specific equations for this particular probability distribution. And of course we will use the parameters. Here the parameters n is number of trials and p probability of success. And the variance is npq, number of trials times the probability of success times the probability of fail. The shape will depend on the values of n and p. So if p tends to 0.5, so it was gonna look symmetric, right? But if p it's like greater than 5, then it's gonna be skewed to one side, or if it's lower than 0.5, it's gonna be skewed to the other side. So the binomial distribution might take different shapes depending of the parameter p, especially. Okay, let's check one example. The probability that a patient recovers from a rare blood disease is 0.4. This is our probability of success right there. That's our P. If 15 people are known to have contracted this disease, what is the probability that at least 10 survive, from 3 to 8 survive, and exactly 5 survive? Alright, so this is 15, it's our N, and 0.4 it's our P. So let me write it down. 15 and P is equal to 0.4. So let's find the probabilities. At least 10 survive. That means 10 or more, right? 10, 11, 12, 13, 14, 15, right? So this is the probability that X is greater or equal 10. So we'll be able to find that probability in different ways. One way is just using the equation. Remember that equation? This equation only works for this equation. It's for one specific value. X equal to 10, X equal to 2, so for specific values, right? It's not giving me like the sum. It's not a cumulative probability. It's just the probability of an exact value. So having said that, let me discuss that there are other alternatives here. If one option is to use the tables of the binomial probability distribution. There are some tables, and those tables will provide the cumulative probability. Or you can use Excel, which is similar to a table. It will give you the cumulative probability. So if you have those tools on hand, and we will use them during the class, then we can rewrite this expression. So one option is, okay, let's do 1 minus the probability of X less than 10, and that will give us as a result the probability that X is equal to 10, 11, 12, 13, 14, 15, right? So we're using the complement idea here to compute the probability. If we're going to use this, follow this path, then we will need the cumulative probability distribution. Remember the CDF? This is the CDF, or FX, right? Remember, capital F to make reference that's our cumulative distribution function. So if we do that, then we will find that the probability of that X is greater or equal than 10 is 1 minus the probability that X is less than 10, which is equivalent to 1 minus the cumulative probability up to 9. Why up to 9 and not up to 10? Because if we do 10 here, then we're going to remove the quality, and that will give us the probability that X is greater or equal to 11. So that's why we're going back one value of the integer values, and in order to do so, then we get the result. So 1 minus 0.9662 is going to give us the probability that 10 or more patients are going to survive. That probability is equal to 0.0338. And as I said, there is another option. If you don't want to use the cumulative, which I highly encourage you to use, then the second alternative is just to compute the probability as x equal to 10 plus probability of x equal to 11. Since there are only 15 people and 15, then the last one will be probability of x equal to 15. And of course, if you add them up, you should get the same answer. We'll practice, as I said, during the class, how to find this CDF using tables and using Excel. Okay, let's check part B. Find the probability from 3 to 8. From 3 to 8. That 3 to 8 people survive. That means 3, 4, 5, 6, 7, 8. So this is the expression, probability that x is between 3 and 8, including them. That's why we have the equalities. When we are in the discrete world, the equality matters. In the continuous case, it doesn't matter, but for now, the equality is important, so you gotta be careful with the equality. So one easy way to find this expression is just to use the CDF of 8 minus the CDF of 2. Same thing than before. It cannot be equal to 3, because if we remove 3, the cumulative of 3, that will remove also the equality of 3. So that's why we go back one integer value, so we make sure that we get the probability from 3 to 8. So do you remember what is the meaning of F8? This F8, capital letter, is the probability that x is less equal than 8. So that includes 0, 1, 2, 3, up to 8, right? And F2 is the probability that x is less equal than 2. So when we make the difference, what we get is the probability that x is between, including 3 and 8. So that's why the CDF, it's important. So this is the first one, is the sum of the equation of the binomial from 0 to 8, is the cumulative. So we're getting all the cases when x is equal to 0, when x is equal to 1, up to 8. And then we're removing, so that's why this sum goes from 0 to 2. So when we remove it, we get from 3 to 8. Here we have the operations, and of course when we end up with the probability of 0.8779. That's the probability that between 3 and 8 patients will survive. And the last one is that exactly 5 patients are gonna survive. So exactly 5 patients, that's the probability of x equal to 5. Since this is an exact probability, we don't need the CDF here. It's just a simple calculation. We just need the equation. So 15 subjects or individuals or patients, we want to find the probability to get 5 successes. Probability of success is 0.4 to the power of the number of successes, right? Because there are 5 successes. This is, remember, the multiplication of the 5 successes. That's the meaning of that 0.4 to the power of 5. That's like 0.4 times 0.4, 5 times, right? Then we multiply by the complement. This is the number of fails. That's the probability of the fail to the power of the number of fails. So if there are 5 successes, then we need the complement, so there are 10 fails. So if you get the numbers, this is 0.18. 5. So that's the probability that exactly 5 patients are gonna make it. Right? Are gonna survive. So this is the binomial probability distribution. Again, there are only 2 outcomes per trial. There are n trials, and what is important here is that the random variable is the number of successes in n trials. This is the last plot distribution that we're going to cover in this video, is the hypergeometric distribution. So it looks similar to the binomial. You got to be careful because the structure changes a little bit. So what's different here? So in the structure of the hypergeometric, we have a batch size n. So we have like a lot of n objects, n individuals, and inside those n objects we have like some of them are labeled as k. K of them are labeled. That means that they are like defective objects, or they are objects of one specific type. And of course the remaining section, n minus k, they have a different labels, right? So if k means defective products, there are k defective products, then there are n minus k that are good products, just to give an example. So in the hypergeometric, then we have, as I said, a batch size, but then we pick a sample and we use lowercase n to represent the sample that is selected. And x refers to the number of successes in the random sample. So how many items, how many objects labeled as k are in the sample size. Again, here x refers to the number of successes or number of objects labeled as k that are in the sample. So please note that the structure here is different compared to the binomial, because in the binomial we only have trials and that's it. But in the hypergeometric we have the lot size, which means like all of the objects, and then from those objects we take a sample. So that's different. Right there, that's different. Okay, and there is an equation that it looks abstract at the beginning, but then you will notice that actually we have used that equation in the previous unit. The equation is to find the probability of x successes. So is from the k label items we pick x, the successes, right? Then from the remaining items in the batch, n minus k, those are like the items that are not labeled as the k items. Then we pick the remaining size of the sample size, right? So that's the numerator, and the denominator means the number of possible selections. So if we have n objects in total, capital N in total, and we pick a sample of n, then all the possible combinations is n combination n. I know it sounds a little bit abstract, so let's check an example and you will see that it makes sense now. Of course, we have here the expected value and the variance equations. Okay, in the problem it says lots of 40 components each are deemed unacceptable if they contain 3 or more defectives. The procedure for sampling a lot is to pick 5. So out of the 40 we pick 5 randomly, and the lot will be rejected if one defective unit is found. Now the question is, what is the probability that exactly one defective is found in the sample if there are 3 defectives in the entire lot? So there are multiple things here. First, we need to define our random variable. So it's clearly asking about the finding one defective, right? So it's like number of successes in the sample. So number of defective in the sample. Number of defective items in the sample. Now to understand a little bit better this problem, we have 40 objects or products in total. That's the batch size, right? We know that some of them are defective. To be more specific, here we're told that there are 3 defective in the entire lot. So that means that there are k equal to 3 products that are labeled as defective, right? And of course, then the remaining n minus k, so that means 37, they are not defective. They are not defective, right? Then we know that in the problem, a sample of 5, so this is the lowercase n, is selected, and the question here is asking how many defectives are in the sample. Alright, so we want to find the probability then that there is exactly one defective. So the probability of finding one defective x equal to 1, so one success in the sample. Guys, an important comment here is like the concept of success or fail, it depends on the problem. So here I'm talking about success as a defective, but that's just a definition that I'm assigning. So success is not always a positive thing here. It depends on the problem context. Alright, so x equal to 1. Now, let's try to figure out a little bit more the equation without looking at it. So how many possible selections we can get? So how many sample points we have in the sample space? So we know that there are 40 items in total. And how many are selected? The sample size, right? So 40 combination 5 is giving us all the possible selections that we might get, right? All the possible selections that we may get. Then to find the number of points in which we get exactly one defective, so that will be the number of defective in the lot, in the entire lot. That's, we know that there are k or 3 defective products. Number of successes, so from those k products we're gonna pick x, right? Number of successes, so we take 1, that's our x. So from k we take x. And now from the remaining products in the whole batch, that's 37. Those 37, remember, they are not defective, right? There are 3 defective, but the 37 are not defective. We take the remaining products that are in our sample. So if we're taking 5 in total and x is equal to 1, so 1 defective, then here we're taking 4 that are not defective. 4 that are not defective. That's the equation, guys. That's the equation right here. It looks different, but it's the same thing. So from k, that's from 3, we take 1, we take x. From the remaining, this is 37. We take the remaining part of the sample, so it's 4 minus 1. I'm sorry, 5 minus 1, 4. And we divide over the total number of sample points. So there are 40 products, and we take 5. So that's what we're doing here. And the probability, of course, then we compute it. I have the number here. Let me find it. The number, I'm computing the number. It's 0.301. So that's the probability that we're looking for. Alright guys, that's everything in this video. So just to summarize real quick. Remember, when you are given a problem, the first thing that you need to do is to define the random variable. There may be some confusion between the binomial and the hypergeometric, but the difference is the structure. In the binomial, we just have the sample size, number of rounds. We have number of trials. N is number of trials. We don't have like a different lot size. But when we talk about hypergeometric, we have 2 n's. We have the uppercase N, which represents all the objects in a batch or lot, and lowercase n is the sample that is drawn from that original batch. So it's a different structure, but x looks similar because the number of successes that are found in the n trials in the first one, but in the second one is the number of successes in the sample n. Okay guys, this is everything in this video. I'll see you in the second part.